Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study how the shear stress distribution takes place on rectangular section. The course outcome for this session is related to the number is 4, and it is apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stress, shear stress distributions and failure of beam sections. And the Bloom taxonomy level for this session is applied. Here, shear stress distribution of a rectangular section. In the previous class, we have studied how the shear stress distribution takes place by considering the simply supported beam subjected to uniformly distributed load. So for that, the shear stress level, the parametric formula, the source formula for that section here, it is the tau equal to FA bar times BI, B times I, where F is the shear force and A is area of the section, which is in hatchet section, and Y bar Y is the distance from centroidal of that area to the neutral axis, and where B is the width of the section, I is moment of inertia of the total section. Now this is the shear stress, that is FA bar times BI divided FA bar times F times A bar by BI. Now we are considering the rectangular section having a width B and depth D. Let F is the shear force acting at the section. Consider the level EF at a distance Y. The level EF at a distance Y from the neutral axis. It is from the neutral axis. Okay, now the shear stress at this level is given by the equation, that is tau equal to FA Y bar by IB, where A is the area of section, where A is the area of section above Y, that is the shaded area EF AB or AB EF. This is the shaded section. This is the shaded section AB EF. So this A is, what is that A? That is length into width. The width is the B and length, how much height it is, thickness. How it comes, that it is D is the depth, neutral axis is the half of to AB, that is D by 2, and this Y is the distance from neutral axis to EF. So D by 2 minus Y, it gives the length BF or FB. So area means length is the B and width or thickness is D by 2 minus Y. That's why D by 2 minus Y times B. That is the area of the section. Area of the section above Y. That is the shaded area. The shaded area is AB, FE. Now we want bar Y. How it comes? Bar Y is the centroid of this shaded section to neutral axis. This is the bar Y. Bar Y distance. That bar Y comes, that is the centroid of the shaded section area from the neutral axis. This bar Y comes Y plus this distance. Y plus distance from here to here. Again, this is the distance. Y plus, small y plus, this is. That is the distance is half of D by 2 minus Y. That's why Y plus half of D by 2 minus Y. Then for simplification, if you do Y plus 1 by 2 goes, that is D by 4 minus Y by 2. So Y minus Y by 2, that is Y by 2 plus D by 4. Y by 2 plus D by 4. Then make it half common, then Y plus D by 2. Half of the times Y plus D by 2, that is bar Y. Then why we need all the things? Because the formula for this is FA bar Y by I times B. This A is calculated here, the shaded area. that is B times d by 2 minus y, bar y, we need bar y. Next I, what is that? I is the moment of inertia, that is B d cube by 12, and B is the constant, that is a B. Now after knowing these values, there are what the known values here, A bar y. Substitute in this formula of the pure shear stress formula, the shear stress formula, that is F into A, that is d by 2 minus y times B. What is bar y? Half of y plus d by 2 by Bi. Now this is F by, for simplification, if we simplify that equation, after simplifying that equation, that is F tau equal to F times F into B by 2 d by 2 minus y on d by 2 plus y by Bi, B times I. Now B get cancelled, that is F by 2I times, that is A plus B into A minus B, A square minus B square, that is a d square by 4 minus y square. That's why this tau equal to F by 2y times d square by 4 minus y square. This is the shear stress. F by 2a times d square by 4 minus y square. Now here what is the d? D is the depth, where y is the distance of EF from neutral axis, and I is the moment of inertia of the section, that is the rectangular section. This is the generic formula. If you want at the extreme section, that is AB, when y becomes d by 2, then what is the shear stress? Becomes y equal to d by 2. That means y equal to d by 2, that means the shear stress, if y equal to d by 2, that means that is the shear stress distribution along from at neutral up to extreme edge, that is the extreme AB. Substitute over in the equation, the equation, then what will happen? Tau becomes 0. That's why shear stress is 0. If y equal to 0, substitute y equal to 0, that is at a neutral axis. Y equal to 0 means shear stress tau at neutral axis. That is y equal to 0. Then this means the F d square by 8I. This is the maximum. That's why Q maximum at the neutral axis. At extreme edges, it is 0. That's why the equation, if you join, the shape of the shear stress distribution comes like parabola. Okay, this is the slope equation. This is the source formula for shear stress distribution over a rectangular section. Yes, what we discuss here, that is what from equation, from the equation, that is F equal to tau equal to F by 2a times d square by 4 minus y square. When tau increases as y decreases, or when y increases, tau decreases. That's why when y equal to d, the variation of the tau with respect to y, that is the variation of the tau, it takes place with respect to y square. That is what? It is the parabola. That's where parabolic shape comes curve. So this shows the variation of the shear stress. This curve, this figure B, indicates variation of the shear stress across the section. Which section here it is? A rectangular section. That is what I mentioned here. It is a rectangular section. Now at the top edge, then y equal to d by 2. Then substitute in the formula. If you substitute y equal to d by 2 in the formula of f by 2a times d square by 4 times y square. In that formula, if you substitute y equal to d by 2, then we get the shear stress at the extreme edge, that is 0. And this is the top edge. If you want to do it bottom edge, same, y equal to d by 2. If you substitute in that formula, in the equation, this is the equation 1, suppose. If you substitute in that y equal to d by 2, extreme edges shear stress. That's why at the top edge and bottom edge, the shear stress equal to 0. and at neutral axis y equal to 0. If we substitute y equal to 0, then it comes at neutral axis, that is f by 2, that is f d square by 8i. So this f d square by 8i, where I is the moment of inertia of the rectangular section parallel to x-axis and about the neutral axis, that is bdq by 12. Substitute f in the place of I bdq by 12, then simplify it. Then that simplification comes, that is 1.5 times f by bd. Tau equal to 1.5 times f by bd. This is where the shear stress at neutral axis is the shear stress at neutral axis 1.5 times f by bd, and shear stress equal to 0 at the top and bottom edges. Now that is we know the tau average shear stress equal to shear force by area of section. What is the shear force? F by what is the area of section? B times d. So we know that tau equal to at the neutral axis, tau at neutral axis, that equal to 1.5 times f by bd. This f by bd is nothing but tau average. So now tau neutral axis is equal to tau average. This tau at neutral axis is nothing. It gives the maximum shear stress. So that means where y equal to 0, that means the stress is maximum shear stress. So tau maximum equal to 1.5 times tau average. Now from the equation of tau equal to fa y bar by ib. So a y bar can be calculated. What is the a y bar? Can also be calculated about the neutral axis. So now consider the strip thickness dy at a distance y from neutral axis. So dA, that is area of the strip b dy, and above neutral axis, that is y times b dy. So here the moment of the shaded area above neutral axis is obtained by integrating the equation from between the limits y to d by 2. So moment of the shaded area from y to d by 2, y times b dy. So b is the constant, y to d by 2, y dy, that means y square by 2. So y to dy up to substitution, that becomes b by 2 times d square by 4 minus y square. This is the moment of shaded area about neutral axis. So now this is a y bar. This a y bar equal to b by 2 times d square by 4 minus y square. We know the formula tau equal to f a y bar by ib. Substitute in the place of a by bar this one. Then you can know the difference. Then it becomes, after simplification, this becomes f by 2a times d square by 4 minus y square. This is the equation, generic equation which we got. This is another method of calculating the shear stress distribution. The generic formula for shear stress distribution, that is f by 2a times d square by 4 minus y square. So here we solved by using two methods. One method we solved by using a tau equal to fa y bar by ib. That means what is a, what is y bar y, and all. But here one more thing, and directly we solved here. That means what is the direct solution? The moment of here from equation fa y bar by ib, this a y bar, what is the a and bar by? A y bar is nothing but moment of shaded area. Now this a y bar calculation comes integral of, that is integral of dA y, that is dA area of strip, that is b dy, and moment of area about dA, that is dA into y, that is b dy times dA into y into b dy, that is b by dy, y b dy. So in that manner, after calculation, we got the same formula for both the methods, that is tau equal to f by 2a times d square by 4 minus y square by using both methods. So what is in this, we found that for rectangular section, we got here the formula for rectangular section of for rectangular section shear stress formula is tau equal to f by 2a times d square by 4 minus y square. This is the source formula. In that we got it, this shear stress is proportional to y square. So what is it? When y decreases, shear stress increases. When y increases, shear stress decreases. That's why when y equal to d by 2, the shear stress becomes 0. When y equal to 0, that means that there is a neutral axis, the shear stress becomes maximum. That's why the maximum shear stress observed at a neutral axis and minimum shear stress observed at the edges, at the top and bottom edges. From that, after calculating that, the tau max equal to 1.5 times the tau average, that is average shear stress. Average shear stress equal to F by BD. Now, let us how to apply this sort derived formula in the problems. Now here, a rectangular beam 100 millimeters, a rectangular beam of 100 millimeters wide and 250 millimeters deep is subjected to a maximum shear force of 50 kilonewtons. Determine number 1 average shear stress and number 2 maximum shear stress, and objective 3 shear stress at a distance of 25 millimeters above the neutral axis. Now from this data, the figure we can draw, we can conceive it. Here it is, that is 100 millimeters wide, 250 millimeters deep, and we need the shear stress. It is 125 millimeters, is above the neutral axis, but we want at a distance of 25 millimeters. Now we know the tau average, that is average shear stress equal to F by area, that is F by BD. What is the F here? 50 kilonewton, that means 50,000 newtons by, what is the B? Width is 100, D is 250. The tau average is 2 newtons per square millimeter. We know the relation for rectangular section, maximum shear stress equal to 1.5 times average shear stress. We know we calculated here the average shear stress, substitute in the formula, then we'll get it the maximum shear stress. So tau maximum shear stress in that equation 1.5 times tau average 2, that is 3 Newton per square millimeter. That is the maximum shear stress, 3 Newton per square millimeter. That is the second objective. First objective average shear stress, second objective maximum shear stress. And finally, the third objective here it is, that is shear stress at a distance of 25 millimeters above the neutral axis. Now, the generic formula we have to use. That means y equal to 25 millimeters, where d equal to depth. What is the d equal to? 250 millimeters. And I equal to BD cube by 12. What is the b here? The b in this, what is the b is 100, d cube 250 cube by 12. We know y, we know d, we know I value now after calculating. And F also, the shear force, that is 50,000 newtons. So by substituting 50,000 newtons and also depth values and the distance of the shaded area from neutral axis, all these values after substituting in this formula, the formula is tau equal to F by 2a times d square by 4 minus F square. The observed after substituting and calculating, the shear stress at a distance of 25 millimeters from the neutral axis is calculated as 2.88 newtons per square millimeter. This is the third objective. So thus we have to solve the first objective and the second objectives and also third objectives. Okay, and okay, these are the various objectives we calculated here. Okay, next problem. These are the three objectives we calculated. First objective is average shear stress. What is the average shear stress? That is F by B times D. Next one is maximum shear stress. Maximum shear stress equal to 1.5 times average shear stress. There is another formula for maximum shear stress, that is tau maximum equal to F by 8I times D square. This is the FD square by 8I. That is the maximum shear stress we calculated. That is FD square by 8I at neutral axis. FD square by 8I. Yes. FD square by 8I. From this also we can calculate the way we use it here, tau maximum equal to 1.5 times tau average. But we can also calculate directly. We know the depth, that is 250 I BDQ by 12. We have to solve here. After knowing the answers, all these known values, after substitution, we get the maximum shear stress value. Okay, next problem if you want to solve, that is okay. A timber of rectangular section is simply supported at the ends and carries a point load at the center of the beam. The maximum bending stress, here it is 12 Newton per square millimeter, and the maximum shear stress is 1 Newton per square millimeter. Find the ratio of the span to the depth. Ratio of the span to the depth. So there is L by D. L by D ratio we want. Ratio of L by D. And here the values are given here. It is simply supported at the ends and point load is acting in the middle. And the maximum bending stress value is given here. It is 12 Newton per square millimeter. And the maximum shear stress here it is 1 Newton per square millimeter. These are the inputs. And output is very simple. There is L by D value. So let us begin. So shear stress maximum is given here 1 Newton per square millimeter. Bending stress maximum is 12 Newton per square millimeter. Now we know the maximum shear force for this type of beam, that is F by 2. F equal to W by 2. That is the W by 2 shear force, the maximum. And the maximum bending moment for this simply supported beam having a point load at the center, that is WL by 4. Now what is the tau average? Tau average shear stress equal to shear force by area. What is the shear force? F by area BD. What is F here? W by 2 by BD. That is W by 2 BD. F equal to W by 2 BD. Okay. Next. And the maximum shear stress, we know the formula, the relation between maximum shear stress and average shear stress for a rectangular section is maximum shear stress equal to 1.5 times average shear stress. Now we got average shear stress value, substitute in the formula, then in that equation the tau maximum already given, maximum shear stress 1 equal to 1.5 times W by 2 BD. Because tau average we calculated, average shear stress is W by 2 BD. So W by 2 BD, then from this W by BD, after simplification, it becomes 4 by 3. W by BD equal to 4 upon 3. That is 1.33. Now we know the pure bending equation, that is M by I equal to sigma by Y. M by I equal to sigma over Y. From that sigma equal to M by I times Y. When sigma becomes sigma maximum, when Y becomes Y maximum. Now we know the maximum bending stress. Now that is sigma maximum equal to M by I times Y max. What is M value? Substitute here, that is WL by 4 in terms of width, in terms of load and span of the beam, and Y maximum Y equal to D by 2, and I value, that is BDQ by 12. Then sigma maximum comes in terms of WLBD, that is sigma maximum equal to sigma maximum, that is equal to 1.5 times. Okay, after substitution here, just we should be very careful, that is D equal to D square times, and what is unknown here, W. How to simplify it here, W L by 4, that is L by 8 into 12 by BD square. Okay, this 8 again, 3 times 4, 2 times 4, okay, that is 3 by 2 times WL by BD square. That is nothing but 3 by 2 means 1.5 times WL by BD square. That is the value we got, that is sigma maximum, 1.5 times W into L by BD square. Now we know the maximum stress value, that the maximum stress value is 12 Newton per square millimeter. But yes, maximum bending stress value 12 Newton per square millimeter. 1.5 times WL by BD square. 1.5 times W by BD into L by D. That is 12 equal to. This W by BD value we know. What is the W or BD value? That is 4 by 3. That is 4 by 3. 1.5, 12. What is here unknown? L by D. What is L by D ratio? Length span to the depth. L by D ratio. Thus, we can calculate after simplifying. This is 12 equal to 2 times L by D. Then L by D equal to 12 by 2. L by D equal to 6. This is a very important problem. For that, we need the concepts, the knowledge of shear force and bending moment diagrams, and also theory of simple pure bending equation. Knowledge one should have in order to solve this problem. Now, how we have calculated, let me summarize in this problem. The input parameters for this problem are maximum bending stress and also maximum shear stress, and we have to find out the span, ratio of the span to the depth, L by D, and the maximum bending stress is 12 Newton per square millimeter, maximum shear stress is 1 Newton per square millimeter, and we know the relations, that is average shear stress and maximum shear stress. Average shear stress equal to F by BD, that is F equal to W by 2 shear force. For that, what is the maximum shear force? You have to calculate. So, suppose it is a simply supported beam, is the W at point A, B. This is RA and it is RB. It is a W and at a distance of L by 2. How to calculate the reactions? By using equilibrium conditions, that is RA plus RB equal to W. That is equation 1. And take moments about A, that is moment equilibrium, sigma M over A equal to 0. That is RB into L equal to W into L by 2. Then RB equal to L get cancelled, that is W by 2. If RB equal to W by 2, RA plus RB equal to W, then RA equal to W by 2. RA equal to W by 2 and RB equal to W by 2. Then apply the concepts of sign conventions of the shear force diagram. And if you observe it, the maximum shear stress, that is W by 2, will come at point A, point C and point B if you apply. From those three values, you have to take the maximum shear force value. And also bending stress value, maximum bending moment, that is W by 2 into L by 2, that is WL by 4. We have to find out where will be the maximum bending moment takes place. At the midpoint of the maximum bending takes place, curvature maximum, that is WL by 4. Is this positive or negative bending moment? Yes, it is the positive bending moment. It will come bending curve. The bending curve will become, that is, it is positive bending moment. So positive bending, that is W by 4. After knowing shear force, maximum shear force and maximum bending moment values, that you have to substitute in the shear force by area. That shear force is this W by 2. In this case, maximum shear force is considered as the shear force. Okay, the maximum value. And the maximum bending moment is considered as a moment of resistance. That is M over M by I equal to sigma by Y. What is that? M is maximum, where sigma is sigma maximum, when Y becomes Y maximum. So in that manner we have to solve. Now after solving this tau average, we know the relation between average shear stress and maximum shear stress. So the maximum shear stress equal to 1.5 times average shear stress. Now maximum shear stress value is given here 1.5 times. What is the average shear stress? W by 2 BD. From that we know the relation W by BD. Why we want? Because it will be useful for in calculation. Where W by BD comes, you have to substitute this 4 by 3 value. Now M by I equal to sigma by Y. That is sigma equal to M by I times Y. Then sigma maximum I, if you substitute, here you can see W by BD into L by D. What is W by BD? We calculated that is 4 by 3. Okay, L by D. Then L by D was calculated. So these are very important concepts, and the textbooks are followed for this session, and reference books and also web references. These are the sites. The links are given here. To understand these concepts, one can also refer these textbooks to understand the concepts of shear stress distribution, bending stress distribution, and shear stress variation across the rectangular section. And we studied only up to rectangular section. Suppose if it is a square section, okay, rectangular section you have studied for this case. What is the square section? Okay. Is there any effect of square section? So here, for rectangular FA Y bar by IB, we have studied here the section tau equal to F by 2I times D square by 4 minus Y square. This is the source formula. Now, how it will affect? For a square section, everything is a D only. B equal to D. So the same formula can be used for the square section also. And if we consider from the neutral axis the distance of the hatching at a distance y, the same formula can also be used for square section. Okay. So let me summarize. In this session we have studied what is the shear stress distribution or shear stress variation over rectangular section in that source formula, and what is the shear stress at the extreme section at the top and bottom edges, and the maximum shear stress observed at the neutral axis, and the variation of the shear stress is parabola. That is what the variation of the shear stress is parabola. That is what figure B indicates variation of the shear stress. At the top edge, the shear stress is 0. At the bottom edge, also shear stress is 0. But at the neutral axis, the shear stress is observed maximum. So then, they found out that the relation between maximum shear stress and average shear stress, then the maximum shear stress equal to 1.5 times average shear stress. And by using, after deriving those equations, we applied those formulae in solving the problems, and solved two problems are solved with a different different models. Consider as model 1 and model 2. There's two models are covered. Thank you.